Okay, again, here's a related rates question example that we haven't done one like. And this is going to involve some trig, just looking at the question. Man walks in a straight path at 4 feet per second. So here's our guy walking. There he is. Searchlight located on the ground 20 feet from the path. Okay, let's go here. We got 20 feet here from the path. Is kept focused on the man by rotating. Okay, so and that gives us theta. So I'll draw theta in there. It gives us an angle. And that, ladies and gentlemen, is the rate of change that the searchlight is rotating, because I'm picturing it rotating around and around and around. Okay, so what do we got here? We've got a dx over dt up here, because he's walking away at 4 feet per second. We do know this is 15, so real quick, we can do Pythagoras theorem. Oh, here, we're looking for that guy. We can do Pythagoras theorem. Let's see, hypotenuse squared. And I'm just thinking about, for at the moment, the guy's at 15 feet from the closest point right here. This is the closest point of the searchlight. And he's 15 feet from there. So at that moment, we can also find how far away he is that way. So the hypotenuse squared is equal to 20 squared plus 15 squared. We go and we simplify that. 400, 225, 620, that's 25 feet. So this, ladies and gentlemen, will be 25 feet when the time comes. Okay. Well, let's figure out a formula. I know with that x, we got to use this side here because we do have the rate of change of x. We need to associate it with this angle right here, and I'm looking at the 20 feet, and this is a fixed value. Not that it matters, but let's use it because we didn't have to calculate it. So if I think of a grade 9 trig ratio for right triangles, I'm thinking opposite over adjacent. That's the tan. So the tan of theta is equal to opposite over adjacent. So I get the tan of theta is equal to opposite, which is x. Of course, we don't, x could be anything. We know it's 15 in this situation, but right now it's just x. And the adjacent is a fixed value, so we can put it in as 20. And there's our equation, I guess. That's what it is. I mean, we don't substitute x as 15 in until we're done taking the derivative. That way we can put in the derivative, the rate of change, we can do all that stuff. So we'll take the derivative of this and see where it takes us to anyways. So the derivative of tan theta is secant squared theta times d theta over dt. Well, that's equal to, the derivative of x is 1. So we're left with 1 over 20 times dx over dt. Well, that's even nicer because we don't even have to think about the 15 because it's not going to matter. We're looking for d theta over dt. Here, I'll circle that up. There it is. So the hardest part is doing theta here, but we'll see what we can come up with because we're going to have to substitute into theta. And right now, we don't really know what theta is, but we can find it. That's not a problem. And we do know what dx over dt is. That's all good. So we got that. So let's go. I'll flip the page, and we'll see where we can substitute in here. So we'll add a page. Okay, so again, we've got secant squared theta, d theta over dt is equal to 1 over 20 times dx over dt. Okay, and we wanted to isolate d theta over dt. This is our goal. Okay, well, I'm going to divide out the secant squared. Well, actually, you know what's maybe even easier? It doesn't really matter. But remember, this is the same as saying 1 over cos squared theta. So I think I'm going to do that instead here. Again, it doesn't matter how you isolate d theta over dt, but this is the way that I think it's easiest. Yeah, it's d theta over dt equals 1 over 20 dx over dt. So now I can, instead of dividing secant squared out and stuff like that, I just see it easier this way. I'm going to times the cos squared, up and across here. So then when I'll have d theta over dt is equal to cos squared theta over 20 times dx over dt. So again, we didn't know what theta is. We could go and figure out theta. We could go and solve for theta using right trig, but I think it's a little bit silly to do that when we know that this is 25 and this is 15 and this is 20 right here in our original triangle, and there's theta. That we've got cos. We've got to replace cos right here. Well, cos we know is adjacent over the hypotenuse. So cos theta is equal to 20 over 25. And I simplify that down, I get cos theta equals 4/5. So rather than going solving for theta, we can just get rid of the cos squared. So d theta over dt is equal to 4/5 squared divided by 20 times our dx over dt, if we remember, was 4 heading that way. So times by 4. So if I simplify this, what do we get? 16 over 25. Reciprocal that's times 20. And I guess this 4 right here is just times by 4. Now we can have that nice and simplified out. And you throw that into your calculator, and I believe it's going to come out to 0.128 radians per second. So it's not the easiest thing in the world, and you can do it, like I said, multiple ways. You don't have to replace out the secant squared. That's just what I did. You can go and find what theta is and substitute it in and pump it into your calculator. There's other ways to do it, but I think that pretty much sums up how to do the question. The same kind of question would work for a shadow. Is how fast is the shadow shortening, or how fast is the shadow changing over time? Same ideas. You're going to use some trig. Sometimes similar triangles will work. So there's multiple ways to do it.